Okay, this is where we left the class last class. We talked about we're talking about forecasting, and let me see where I missed my here it is 12. Okay, so we said what the form of these forecasts are going to be for series that are not stationary, and so we're working with the transform series, and we make it stationary by taking differences. Okay, so with the model, once we take the differences, we have we say the polynomial if it's the original model is a PQ. Once we have the differences, this phi of B polynomial is further P plus D, right? P is the number of autoregressive terms, and D is the number of differences. So this is the expression for the forecast H periods ahead, and that'll be the optimal forecast H periods ahead. And the thing that's important here is that for all the theory behind these forecasts, we're always using the trick of dividing what's history and what is the future, so that we can calculate the conditional expectation, which is the optimal forecast. Okay, so we said that the expected value of the conditional on T of the transform series H minus J G periods ahead is going to be the actual value if we are in the past, and it will be if J that is J is greater than or equal to H, and T of Z that will be the actual value, and this is the forecast. Okay, this will be the forecast, the optimal forecast in essence. Let's look at an example. Let's take this process. It's an ARMA 1-1 process, ARIMA 1-1-1. So we have one autoregressive term, that's 0.6 times B, one difference only, and that with the transform series T of ZT. Okay, so we're working with that transform series. We probably took a log or whatever, assert some box and Cox transformation to make the variance constant, and we have an MA1 and one order moving average polynomial, and that's it. So we express now T of ZT plus H as 1.6 times T of CT plus H minus 1, because of this equation here, minus 0.6T times ZT plus H minus 2 plus AT plus H plus 2.28T plus H minus 1. Okay, so that will be the expression for the transformed series at period H T plus H. Okay. Okay. So all we did here is replace write this equation as 1 minus 0.6b times 1 minus b T of CT equals to this thing here, and then put everything on this side, leaving only the T plus H value of the transform series on the left side of the equation. That's all we did. Now, based on what we saw yesterday, the forecast starting at origin T, so we have all the data of 2 times T, and the forecast of the optimal forecast 1 period ahead of the T of ZT 1 period ahead is 1 point. I just use this expression, this expression here, and replace it. It's 1.6 the conditional expectation of the transformed series. Okay, because that's we're talking about the optimal forecast, right? Minus 0.6 the conditional expectation of T of ZT minus 1, which comes from this term, and then plus the conditional expectation of AT plus 1 plus 0.2 expected conditional expectation of AT. So we're doing this is H equals to 1 in this case. Okay. Now this is what's this? The transformed series at time t, we know that conditional expectation because we have that observation. We are time t, so we know what t of zt is. So it's 1.6 t of zt. And then the next term, we have zt minus 1. It's already in the past, right? So that will be minus 0.6 t of zt minus 1. The conditional expectation is the actual value because we already know it. Then we have 0.2, the expected value of t of zt minus, because that's the expected value of this thing here. At, we already know At, and At is this thing, is the difference between the forecast one period that we made the previous period, the forecast that we made one period ahead yesterday. Okay, the forecast that we made yesterday for today, and then I take the difference between that and the actual value for today, which I already know, and that's my estimate of At. So the expected value is that, is what I already observed as At, which is the forecast error. Okay, if we go now for h equals 2, we're going to go 2 periods ahead. Then what we would get is what? Here I will have, if h is equal to 2, then I will have 1.6 t of zt plus 2 minus 1. So it's 1.6 times t of ct plus 1, and that's in the future. So that will be the optimal, and that's the conditional expectation, okay, something in the future. That conditional expectation is the optimal forecast, t hat, of zt one period ahead. Then the next term is minus 0.6 t of ct when h is equal to 2. We have t plus 2 minus 2, that's time t. So we know the actual value. We know that that's 0.6 t of zt, because we know what ct is. And then the other term, expected value of At plus h for h equals to 2, that's 0, because that's in the future, and the noise, white noise has 0 mean. And then 0.2, expected value of At plus 2 minus 1, which is At plus 1, that's also in the future, so that's 0. So all I have for period 2 is 1.6, the optimal forecast, one period ahead, minus 0.6, the actual value of t of zt. And in general, if h greater than or equal to 3, we will get 1.6 t hat, the optimal forecast, h minus 1 periods ahead, minus 0.6, the optimal forecast, h minus 2 periods ahead. So once, if h is equal to 3, then I would have here t plus 3 minus 1, that's t plus 2, that's in the future. So the conditional expectation is going to be the optimal forecast. And then I have 3 minus 2 is 1, so it'll be t plus 1, zt plus 1. The conditional expectation of t of zt plus 1 is the optimal forecast at one period ahead. And h is equal to 3, so that'll be h minus 2. And the other terms are going to be 0 because they are already in the future. So those the other terms are 0. So as you can see, the forecast at h periods ahead, the optimal forecast depends on the optimal forecast h minus 1 period for h minus 1 periods ahead, and the optimal forecast h minus 2 periods ahead for h greater than or equal to 3. Okay. So the forecasts for h greater than or equal to 2 follow the behavior given by the difference equation that defines the model. Okay, the difference equation is this one here. Remember, the difference equation is 1 minus 0.6b times 1 minus b t of zt. And that polynomial is 1 minus b minus 0.6b plus 0.6 b squared t of zt, right? So that's 1 minus b minus 1 minus 0.6b is equal to minus 1.6b is 1 minus 1.6b, and then minus 0.6b squared, which is this polynomial here. Okay, so that equation is determining the behavior of the forecasts for h greater than or equal to 2. Okay, it's that's what determines the behavior. Where now b is operating on h. Okay, so when we apply b to tc plus h, we're operating on h, on the number of lags that we are forecasting ahead. Okay, so if we generalize this thing for any h and for any polynomial phi of b, which is phi of b difference, okay, we generalize that to that polynomial, then the optimal for the conditional expectation, the optimal forecast of ct h periods ahead is the conditional expectation of t of ct h periods ahead. Okay, that will be the conditional expectation, and that's going to be in general equal to phi 1, the conditional expectation of t of ct plus h minus 1, plus all the way up to phi p plus d, because we have p plus d terms in this polynomial, in this product of these two polynomials, we have p plus d terms. A conditional expectation of t of ct plus h minus p minus d, because we lose p observations because it's an autoregressive order p. That means that we need time. If we are time t, we need t observations t minus 1, t minus 2 up to t minus p. But since we took d differences, we need also t minus d minus 1, t minus 2, t minus p, and t minus p minus 1 up to t minus minus p minus d and plus h, whatever h that is. Okay, so that's the conditional expectation, because we're talking the optimal forecast, and then the conditional expectation of at plus h, and of course for h greater than or equal to t, greater than t, for h greater than greater than or equal to 1, sorry, this will be 0. This expected value will be 0. So this equation results, if you work out the expectation, the conditional expectation, then it will turn out that this optimal forecast is going to be phi 1 t of zt plus this whole polynomial minus the moving average part multiplying the ATs that we already know. Okay, so whatever is in the past, when we are talking for h equals to 1, all these the only AT involved here is AT time 8 at the error time t, which is known because we know for h equals 1, that will be the optimal forecast, 1 period ahead, subtracted from this the actual observation at time zt. Okay, we know zt, so we know t of zt, and we just subtract what we forecasted for ct 1 period before. Okay, for 2, it's the same equation, but now we have it involves the forecast 1 period ahead, the optimal forecast 1 period ahead, plus 5p plus d, t of zt plus 1 minus p minus d, and so on. We're forecasting now 2 periods ahead, so you just replace a 2 here in this equation, and you will get this thing. Now I do not have an AT, because for h equals to 2, I no longer have that last term, and all the way up to the qth forecast. Okay, the all these forecasts, 1 period ahead, 2 periods ahead, 3 periods ahead, involve the coefficients of the model on the autoregressive part, including once we multiply by the number of differences, by the difference, and then includes also the moving average coefficients, the phi 2, theta 2, theta 1, theta 2, theta 3, and so on, up to theta q. Up to the q lag, we still have one of the coefficients of the moving average polynomial that intervenes in the forecast, multiplying the error at time t, which is estimated as the forecast 1 period ahead that we did the previous period. But after we go for more than q periods, after h is greater than or equal to q, then the moving average terms do not appear anymore in the forecast. The forecast only depends for h greater than or equal to q plus 1. The forecast only depends on the coefficients on the autoregressive side of the equation. Okay, that has phi of b times the difference of or 1 minus b to the d. View here. So in general, after we exceed the order of the moving average polynomial, then the forecasts are determined only by the autoregressive polynomial. Okay, that's what determines the forecast, and it involves the forecasts, the optimal forecast that we have h minus 1 period ahead, h minus 2, up to h minus d minus p minus, or h minus p minus d minus 1, which is this last term. Okay, so that polynomial, that autoregressive polynomial determines the behavior of the forecast for periods ahead greater than or equal to q plus 1, where q is the order of the moving average polynomial. Okay. Are we clear up to this point?
Yes, teacher.
Okay, great. Now, remember the optimal forecast of zt h minus j periods ahead is t of zt plus h minus j if j is greater than or equal h. Okay, if j is greater than or equal h, because if j is greater than or equal to h, we are in the past. So the optimal forecast is what we already observed. For example, if j is equal to, if h is equal to 1 and j is equal to 1, we'll have zt. If h is equal to 1 and j is equal to 2, then we'll have zt minus 1 and so on. Okay, so that's already in the past. So this then is given by the difference equation phi of bt by the polynomial, the backward polynomial, backshift polynomial given by this expression is equal to 0. And the solution for this polynomial, for this equation, involves the initial conditions, and the initial conditions are the only ones that involve the q parameters from the moving average side of the equation. Okay, so the q parameters of the q moving average parameters only intervene to fix the initial conditions for the forecasting process. Okay. Once we exceed q, then those initial conditions, we forget about them, and it's all that all the behavior of the forecasts is driven by the autoregressive polynomial. Okay. Now, one thing that's important to do is to compute confidence intervals for the forecast. I mean, we know, we saw now how we obtain a point forecast. Okay, what's the observation that I'm forecasting 3 periods ahead, 4 periods ahead, and so on. But there's an error associated with that forecast because we do not know the true value of the parameters. we don't know the phi's. We are going to estimate the phi's. So we need to put a confidence interval to the forecast to see how much uncertainty we have when we forecast 1 period ahead, 2 periods ahead, 3 periods ahead, and so on. The conditional expectation of the forecast error h periods ahead is 0. Okay, we've seen that already. So the variance is the expected value of these things squared, the errors squared, the forecast errors h periods ahead squared. And we already saw that that variance is equal to the sum from j equal to 0 to h minus 1. We're forecasting 3 periods ahead will be the sum from j equal to 0 to 2 of the psi weights squared times sigma squared. See, because the variance for the a's is constant, the sigma squared. So we just have the coefficients for the expression of the model are the psi weights. So the psi weights squared times sigma squared. And since we're assuming that the ATs are independent and are normally distributed with variance sigma squared, then the forecast error h periods ahead, given that we know ZT, CT minus 1, and so on, all the past, starting from ZT, will have a normal distribution also with mean 0 and variance conditional on T. The variance, that's why the subindex here, T means it's a conditional variance of the error, the forecast error h periods ahead. Okay, so that T of ZT plus H minus the optimal forecast, which are the errors, okay, these are exactly the errors. Okay, this is the actual value minus its forecast, given that we know ZT minus 1 and so on, will have a normal distribution with mean 0 and variance given by the conditional variance of ET of H periods ahead. For the forecast error, forecast that I make when I forecast at time T, H periods ahead. That will be the variance, okay, of these forecast errors. So that if we want to build under this assumption of normality, a 100 times 1 minus alpha % confidence interval for the forecast, for the true value of T of ZT plus H, okay, the confidence interval for T of ZT plus H, we can compute that using the percentiles from the normal distribution. So if it's a 95% confidence interval, then alpha will be 0.05, and it will be the tail end of the normal distribution that gives an area of alpha over 2, which is 1.96, right? If it's a normal distribution, standard normal distribution, it will be 1.96 if it's a 95% confidence interval, times the variance times the standard deviation of which is the square root of this whole thing. So we just take the sum squares of psi sub j squared times to the 1/2, okay? And here it should be sigma and not sigma squared, okay? This is sigma because it's 2 times the standard deviation. So in essence, this is approximately the optimal forecast of ZT H periods ahead, plus or minus 2 times the standard error, and the standard error is nothing but the sum of the psi j squared times sigma, which is what we have here. Okay, that will be the standard error. Okay, and that's how we build the confidence intervals for the H periods ahead. Now, if you look at this expression here, one thing that it becomes clear, let me make the correction right now so that I cannot find my, oh, because I'm blocking it with this screen here. So what is clear is that if we look at this equation, the larger H is, the larger this confidence, the wider this confidence interval is going to be. Because these are positive numbers, we're just adding, if H increases, if H is equal to 2, then we're adding to psi 0 and psi 1 squared. Okay. If H is equal to 3, that'll be from J equals 0 to 2. So that'll be psi 0, which is 1, psi 1 squared plus psi 2 squared. So I keep adding positive numbers so that the multiplier for this standard deviation of the A's is going to be keep increasing for larger values of H. So the confidence intervals, the farther away we are from the point of that we are from where we are forecasting from point T, from time T, the farther away we forecast, our confidence intervals will become wider. Okay, which is natural because the farther away that I forecast, the more uncertainty I have about what the true value of that forecast is going to be. The other thing is that that's important to note is that this is valid for a given value of H. Okay, so if H is equal to 2, this is valid for H equals to 2. If H is equal to 3, that's valid for H equals to 3, and so on. It's not valid for a set of values of H. That is, what I get are confidence intervals and not confidence bands. That's a big difference. What this is saying is, let's suppose this is my series. Okay, and then I'm going to put my forecasts. This may be my forecast, and for each forecast I have a confidence interval that gives me for this forecast is this is the interval. For the next observation, it's this interval, and for the next observation is this interval, and so on. Okay, so the intervals will keep getting wider and wider, but these are not confidence bands. It's different to have separate confidence intervals than to have confidence bands. Okay, because we're not using the joint distribution of the future z's of the zt plus 1, ct plus 2, ct plus 3. We're not using that. That is, we're not using the joint distribution of at plus 1, at plus 2, at plus 3, and so on. So this is intervals and not bands. If that's a different thing. Okay. A band, if we were to compute a band, then that would mean that we would have something like this. Let me choose a different color here. If these were bands, then we'll have something like that maybe. So that means that the forecast will fluctuate around these bands, but we cannot say that. What we can say is that the T plus 1 observation, the 95% confidence interval for the T plus 1 observation is this one. And the confidence interval for the T plus 2 observation is this one here. So, but these are different from confidence bands. Actually, confidence bands would be actually wider in general. Okay. The individual confidence intervals. Now, we do not know the psi weights, so we need to estimate them. The estimate of the psi weights come from the estimates of the parameters for the autoregressive parameters and the moving average parameters. Because what we know is that if I take phi hat of B times psi hat of B, that will be equal to 1 to theta of B, theta hat of B, which is a moving average polynomial replacing the parameters by their estimates. So the way we obtain the psi weights to compute the variance and of the forecast errors is going to be by multiplying these polynomials and grouping factoring with according to the power of b, and then equating the coefficients. Okay, so what we do is we factor in terms of b with all terms that involve b, all terms that multiply b to b squared, all terms that multiply b cubed, and so on. And we equate the terms that multiply b here with theta 1 hat. We equate the terms that multiply b squared with theta 2 hat, and the terms that equate that multiply b cubed for the terms the theta 3 hat, and so on. Equating those coefficients is how we solve for psi hat. And then psi hat will be given by, and this is again just algebra, psi hat will be given by theta hat sub j plus phi 1 hat psi j minus 1. But I'm going to stop saying the psi hat, and there are too many hats here. Okay, these are the estimates. So this is, or we're dealing only with estimates here. So it will be theta j plus phi 1 psi j minus 1 plus phi 2 plus phi 1 psi j minus, I repeated the term, that will be phi 2 the psi j minus 2, and so on, all the way to phi p plus d, because we have p autoregressive powers. I mean, the autoregressive polynomial phi is of order p, and then we have d differences, so we go to p plus d times psi j minus p minus d. That will be equal for j equals 1 through q. Okay, so for j less than or equal to q, which is the order of the moving average polynomial, this expression here will give me the jth weight to be able to compute the variance of the forecast errors, to estimate the variance of the forecast errors. And then once j takes the values q plus 1, q plus 2, and so on, remember when j takes values greater than or equal than q plus 1, then the q term, the q moving average terms stop appearing, right? There, I don't have moving average terms for my forecasts when I go beyond q. So my cj hat will be equal to this thing here, and it ends here in j minus p minus d. Okay, for j greater than or equal to q plus 1. Since we assume that psi 0, we defined that psi 0 is 1, so psi hat 0 is 1. Okay, and psi j minus I hat will be 0 if j is less than I, because we're only involving the psi weights up to the cube observation of the up to the cube psi weight. So that's it. That's how we get the psi weights to compute the variance of the forecast error. Now, to estimate the forecast precision, we recall that thing is the variance of the forecast error h periods ahead is this thing here. We brought this is the same equation we saw a couple of slides before. Then if the model is only a moving average model, so if it's an MA model, I don't have autoregressive terms. Okay, if it's an MA model, I don't have autoregressive terms. So the variance, which is j from j equal to 0 up to q. Okay, the h periods ahead, the variance will be the sum of these weights sine sigma squared from j equals to 0 up to q for h greater than or equal to q plus 1. So as long as I'm forecasting more than the order of the moving average polynomial, this will be the variance of the error. Okay. So that if you look at this thing, then this variance is bounded, right? This variance is bounded. So if h increases as h tends to infinity, if I wanted to forecast many periods ahead, once I get to h greater than or equal to q, the variance doesn't change. So the variance is going to be bounded. So the confidence intervals will look like constant after for h greater than or equal to q plus 1 in an MA model. Okay, I don't have autoregressive terms here. It's on an MA model. Now, what if we have an ARP model, an autoregressive model of order P? Now, if it's purely autoregressive model, we already saw when we studied the autoregressive models that to solve the difference equations of order P greater than 2, we consider this equation, okay, which is essentially, this is representing the autoregressive polynomial equal to z0 to the constant, okay. If we solve this equation, there's a theorem, the algebra's fundamental theorem that you may remember. Then any polynomial can be written as the product of 1-degree polynomials. Okay, so if it's a polynomial of the order P, I can express that polynomial as the product of P polynomials of order 1, and I obtain the pth degree polynomial. So if we call the constants for each of the terms in this expression to represent this polynomial, g1, g2, and so on, and we call that g of b, the backsheet polynomial g of b, then the roots of this equation, the roots of the corresponding characteristic equation for the autoregressive model, will be g1 inverse, g2 inverse, because any of these values will give us a 0. Okay, so that the roots of that equation are going to be g to the minus 1, g1 to the minus 1, g2 to the minus 1, up to g sub p to the minus 1. If we assume that all the roots are distinct, that may not be the case. Some roots may be the same. But if we assume that all roots are distinct, then the general solution can be written in this form. I can write the general solution as zt of this equation. Okay, the general solution of this equation can be written in this form as z0, and then I put this dividing, plus s1 g1 t plus g2 t plus gp to the t, and s1 up to sp are the constants which are determined based on p initial conditions. We have order p, autoregressive polynomial. Then the constants that determine this solution are obtained through p initial conditions. Okay. Now, if we use the series representation as a random, as a linear combination of random shocks, which is a representation that we've seen for stationary processes, we express Ct as psi of b applied to At times I'm sorry, and for psi of b is the usual thing, is psi 0, which is 1, plus psi 1 b, psi 2 b squared, psi 3 b cubed, and so on, all applied to H sub t. If the model is an AR, an autoregressive model of order P, and the roots of the equation are these numbers, these distinct numbers, G1 through GP, then the weights, the psi weights, can be written in this form. Psi j would be equal to S1 G1 to the j plus S2 G2 to the J plus SP, where the G's are the G's are the G's from the polynomial, okay, from the that were used to represent the polynomial as a product of P polynomials of order 1. Then the weights can be written as this equation. So if we now use the sum of sides to J squares from J equals 0 to infinity, we split that sum in two parts, the way we did before. But now we split it in the psi weights up to period P minus 1, okay? And then the psi weights from J equals to P to infinity. And that will be the sum. This term remains, we keep the same term here. But this term, we can express it as the sum of S1 G1 to the J plus S2 G2 to the J plus SP G sub P to the J, this whole thing squared. Okay. So from here, if we compute the variance, we will multiplying the variance of the error, the forecast error, we will multiplying by this whole thing here. And then if G sub I is less than 1 in absolute value, that is, if we're talking about a stationary process, so that the roots of the polynomial are greater than 1, okay? The roots of polynomials are greater than or equal to 1, so outside the unit circle. Then the infinite sum of these things will converge, okay? This infinite sum will be bounded by the sum of the SIs from J equal to P to infinity, okay? That will be bounded for these things squared. So there's a bound to this. When we compute the variance, that variance will be bounded, but now it will keep growing, right? So when we take the limit now, that's also just replacing the equation from the last slide from this one here. The limit when h tends to infinity of the variance conditional on t. It's always important that when we compute the variance or the expected values, we are conditioning on t, that we know that all the data up to time t. Then the variance of the forecast error h periods ahead will be equal to the sum of the psi j's sigma squared, but this will be bounded by the sum, because we have, remember, that's this sum we express it in these two terms. So the variance will be bounded. One slide. Will be bounded by the sum up to P minus 1 of psi sub j squared plus the sum from I equals to 1 to P of S sub I squared times sigma squared. So the forecast beyond P minus 1, the variance will tend to be constant. Though it's not constant, because if you look at the variance, this sum is infinity. It's a sum from J equals to P to infinity. But this is bounded by this sum. So the bounds, the forecast beyond P minus 1, its variance will tend to be constant in the long run. In the long run, once we exceed P minus 1 periods, the variance will tend to be constant. Will not be constant as it happens in the moving average, in the pure moving average case, but will tend to be constant. Will not grow too much. The variance will tend to converge to. If you look at confidence intervals, the confidence intervals will converge to something that seems to be constant, at least in the very long run. So that's the case for an AR model. So for an MA, the variance will become constant after some time. After we exceed Q, the order of the moving average polynomial, the variance will become constant, so the confidence interval will remain constant. For an AR, they will not remain constant, for great values greater than P, but they will tend to be constant. Now, for an ARMA PQ, the psi j's can be written as S1 G1 to the J up to S of P GP to the J, which represent the P initial conditions, for G, J greater than or equal than the maximum between -1 and Q. Okay, so whatever is greater, either P minus 1 or Q, for values of J greater than that, the Jth weight will be equal to this thing here, okay? The Jth weight. And that, if we use now the expression for the variance of the forecast error, then the forecasts beyond this maximum will tend to have approximately the same precision, okay? Because the variance will tend also to be constant after we exceed the maximum between P minus 1, P being the order of the autoregressive polynomial, and Q. Okay. That's for an ARMA PQ. Now, if we have an ARMA PDQ, that is, if we took differences, then if we took differences, remember that when we take differences, we're taking phi of B, right down here, we're taking phi of B times the difference, and that's phi of B. This polynomial no longer has its roots outside the unit circle. Okay, this one, if this one has its roots outside the unit circle, but this one is not. The root is 1. Okay, the root is the value 1. So when you multiply two polynomials, the roots would not be outside the unit circle. Okay, so that's a big change in the ARIMA PDQ. Because in the ARIMA PDQ, so the jth weight, the psi weight of order J, will be equal to this expression: S1 plus S2J plus SD to the J to the D minus 1 plus SD minus the SD plus 1 G to the AD plus 1 raised to the power J, and these other terms are all multiplying G to the power J, and those will be greater. That will happen. The size of J will be given by this, as long as J is greater than the maximum between P plus D minus 1 and Q. Now we have to consider D. Remember, before we only had P plus D. Now we have, and actually we're looking at P minus 1, right? That was the bound. Now here we have the maximum between P plus D minus 1, because we have to subtract it's P minus 1 or P minus 1 or the original parameters in the autoregressive polynomial, plus D now, because that polynomial, this phi of B is for the P plus D, so have P plus D minus 1, and Q. If J is greater than or equal to this maximum, then that will be the weights, so that the limit when J tends to infinity of psi sub J squared is different from 0, and that will imply that psi sub J squared diverges. This is psi sub J squared diverges because these weights, since this is no longer, this polynomial is no longer has its roots outside the unit circle, then the sum of the squares of psi sub J, the sum of the psi sub J squares, will not converge, because this is not stationary. So since this sum diverges, what that means is that the variance of the forecast error H periods ahead will tend to infinity. So in this case, the confidence intervals will always be increasing. Okay. In the other two cases, the confidence intervals will tend to be constant, and the autoregressive tend to be constant. In the moving average will be constant after some periods of time. But for the ARMA PDQ, since we are taking differences, then the forecast errors, their variance will not tend to a constant and will grow to infinity. So in these cases, confidence interval will keep growing as we get away from the time t where we're doing the forecast. Okay. So that's important when you because it tells you what to expect depending on the model, what to expect of the precision of the forecast when time grows on, when age increases. Okay. So in the autoregressive part, or in the moving average model, or in the ARMA without differencing, or in the ARMA model, these confidence intervals will eventually tend to be constant. Okay, and the MA will be constant, but in the AR case or the ARMA PQ case, they will tend to be constant. But when we take differences to make the series stationary, then the forecast their confidence intervals will tend to increase as age increases, will increase. Now, the other thing that we should consider, and that's important, is that let's suppose we are today and we are forecasting tomorrow. Now let's move to tomorrow's day. Now, tomorrow I already know the information for tomorrow, so the forecast that I made for tomorrow is meaningless now because I have the actual data. So as soon as new data comes, is observed, as soon as the future data is being observed, then the forecast that we made before become their validity, lose their validity because we already have the actual data point. So the forecasts need to be updated. And there's a couple of considerations here. We can, with the same model, keep updating the forecast when we get new observations. The other thing that can be done, and actually is more practical, it's what we should be doing, is to re-estimate the model when new data come. As soon as we start getting new data, we need to re-estimate the model, and we need to validate the model again. Suppose we're working with monthly data. Okay, so I'm working with sales data. So I have sales up to last month, September, and I forecasted my sales for October. Once October is over, I will know what the sales for October are. So I could just update the forecast for November if I don't want to recompute the model. And that was a whole issue when computers were not that easily available, because if I needed to re-estimate the model, sometimes it was painful. Especially when these things started, when the theory started developing, where a lot of these computations had to do almost by hand or very basic computers. So the forecasts were updated. But nowadays, it doesn't make sense to just update the forecast. What makes more sense is once I have October, I re-estimate the model, including October, validate that the model is still valid because models can change over time, and then do my forecasts again. Okay, that would be the right thing to do. Now, if we just wanted to update the forecast, then this is what we would do. If we want to update a forecast once a new observation arrives, we can use the fact that the conditional expectation, the optimal forecast, which is the conditional expectation at time t of tct plus h, is, we already saw that's minus the sum from j equals to h to infinity of the psi sub j at plus h minus j. And that's the optimal forecast, and that's the optimal forecast at time t, h periods, h plus 1 periods ahead, minus the last weight, the h weight, if we're forecasting h periods ahead, the h weight times at plus 1. So now that I have the T+1 observation, I can update my forecast taking the forecast that I made at time T for today and subtracting the H weight multiplying the AT+1 error. Once I have AT+1, once I have CT+1, I can compute AT+1 from the forecast that I did the day before, right? So for example, suppose that we forecasted H values of T of ZT. So we were at time T and we forecasted capital H values starting at origin. And let's change the origin to origin N. Now I'm at origin N. So my last observation was the nth observation. That was yesterday. So yesterday I forecasted capital H periods ahead. So yesterday I forecasted today's sales, tomorrow's sales, day after tomorrow's sales, and so on, the next 7 days of sales. Okay. Then my optimal forecast at time N, 1 period ahead, that is the forecast that I did yesterday. The optimal forecast that I did yesterday for today is this would be the optimal forecast, right? This will be the optimal forecast at time N, 2 periods ahead for tomorrow. And that will be then the optimal forecast for day after tomorrow, and so on up to the 7th day. Those are the original forecasts that I computed yesterday. Now over today, we observed N+1. We observed Zn+1. Since we observed N+1, we know what An+1 is, because An+1 is today's observation, which is T of Zn+1, minus the forecast that I did yesterday for today. That will be An+1. That's the forecast error based on the forecast that I made yesterday for today. And I can compute this thing now because I know this estimate. I computed that yesterday, and this observation came up today. So we can re-estimate the following forecasts with origin N+1, updating the forecast that I have. So if I want to update now the forecast that I have made at time N+1, 1 period ahead, all I have to do is take the forecast that I did before 2 periods ahead and subtract psi1 times An minus An+1, because I already know this thing, right? And I just multiply it by psi1, and then I update my forecast, the forecast that I had made for tomorrow, I update it based on the forecast that I did, based on the actual error, the AT, the An+1 that I observed today. Then the forecast that I do now at N+1 today, 2 periods ahead, I take the forecast that I did yesterday, 3 periods ahead, which is this one, and subtract psi2 times An+1, because well, I know An+1 now. So I update all forecasts based on today's error, because I already know today's error once I have today's observation. All the way up to the forecast that I made, the forecast that I make now, which is N+1. H periods ahead, it will be H minus 1 periods ahead, because if I was originally forecasting up to next Saturday, up to next Saturday of next week, now I will be, if I did that forecast yesterday, right? I was forecasting up to Saturday of next week. That was, let's say I was forecasting up to, today is what? Today is Friday. I was forecasting up to Friday, right? Next week. Yeah, I forecasted yesterday from today to next Friday. That was 7 days. Now, Today, I will forecast 6 days. So because if I will forecast from here, I will forecast until next Thursday, next Friday. So I will forecast only Saturday, Sunday, and so on up to Friday. That'll be 6 days. So H minus 1. My forecast H minus 1 periods ahead will be the forecast that I did yesterday, H periods ahead, minus psi H minus 1 times AN plus 1, which is what I determined today, because today's observation already arrived. So that's a way to update the forecasts with the same model. Okay, we already have the same model because we're using this. And of course, we don't know the size. We're estimating the estimated size. But again, the best thing to do is, if I have today's information and running my model takes a couple of minutes, then I run my model, including today's observation, validate the model again, and then recompute my forecast. Okay. And what happens in practice, in fact, is that we have usually a moving window. Okay. For example, I have, let's suppose that I have monthly data. Let me clear the page. Okay. Let's suppose that I have monthly data, and I have data from 2019, January, then we have 2019, February, and so on, 2019, month 12, and then have 2020, month 1, and so on, and all the way up to 2020, month 12, and I have 2021, month 1, up to 2021. Right, I was going to erase the whole thing. 2021, last September, right? Let's say I have I was using commas here. Month number 9. With this, I estimated the model and I forecasted 2021, month number 10, 2021, month number 11, all the way up to 2000. Suppose I forecasted only 3 months, 11, 12, and I forecasted 2021, 12 months. Okay, I forecasted that. Now, once I have the data from, the data from 2021 of month 10, once this becomes available, what we should do is, what normally is done in practice is we shift, and now I take these months and I add the last observation, 2021, month 10, remove this one. It's not necessary, but that's what usually doing. We have a window of 12 months, of 24 months, let's say, or 48 months, let's say, for example, that I keep moving. So as a new month comes in, I eliminate the first month that I had and replace it at the end by the information from the month that just came in, the information, recompute the model, and then I would forecast. I don't need to forecast that, so I would need to forecast now 2021, 2022, month number 1. Okay, so we usually moving windows, and we keep moving. How many periods ahead do we forecast? Depends on what we need. Let's suppose that you're doing a forecast for raw materials, and you need to forecast raw materials, and you order a certain raw material. You may place an order a month. If the supplier takes 1 month to deliver the material, then you would have to forecast, to be safe, at least 2 months ahead. Okay, so that you know the forecast and you can communicate the forecast and you can get the material on time. Okay, but if the lead time to deliver the material is 3 months, then you need to forecast 4 months ahead and so on. So how many periods ahead? It depends on the situation. But that's the best thing to do. Just re-update the model, calculate the model again, validate it, and do the forecast. Now, how we measure forecasting capability or forecasting accuracy, for example. Once we build a time series model, we can study the forecasting capability of that model once we get the actual values, right? When we have the actual values, we can validate how good the forecasts that we computed before were. We can validate that way. The forecasting error, to measure forecasting error, there are essentially two ways to measure forecasting error. The first one is we build H forecasts starting at origin T, capital T or whatever. That's a tau. That's a tau that didn't come that nice. We build H forecast starting at time tau, which is n minus H. So we build the model. Let's if we are going to be forecasting 6 months ahead, then the ideal thing is we take our history that we have, and let's suppose I have data from 2015 up to now. So I remove the last 6 months because I'm going to be forecasting always 6 months ahead. So before I use the model, first I computed with the previous data, leave 6 months that I already know the data points from those 6 months, build the model with the n minus 6 months of data, forecast the 6 months that I already know, okay, and then compute the error for 1 month ahead, 2 months ahead, 3 months ahead, based on the data that we already have. So we compute the differences between what we observe actually and what we forecasted we were going to observe. Then that's one way to evaluate the forecast. Okay, take those errors. That we'll call that E of tau if H periods ahead. Okay, that's called dynamic simulation. I remove the last 6 months, build a model with all the data before the last 6 months, forecast these 6 months, and I compute the errors on these 6 months. That's dynamic simulation. Another way is what's called static simulation. So we have a single value that we forecast starting at different origins. So let's suppose that I am forecasting 6 months ahead, and I'm in June. I take my data up to December, the historic data I had to December, then up to, let's say, December. I forecast 1 period ahead, and then compute the error for that forecast 1 period ahead. Then I move my endpoint 1 period. So I now build a model up to T plus tau plus 1 and forecast tau plus 2 and so on. But it's always forecasting a single value at different origin time, at different origins. That's called static simulation. Then we would always compute here the error 1 period ahead starting at different points in time. Okay, that will be static simulation. Then based on the error, whichever method we use, if we use the first method, we're going to call this thing here M1. We can calculate the average of the errors. Okay, but that's not a good idea. Now we'll see why. And M2 will be the average of the errors in the second method, in the static method. Okay. In either case, we're just taking the errors and averaging them over the H periods that we used to test the accuracy or to see how good the model is for forecasting. Then the error as such is not a very good measure because they can cancel themselves and so on. So what is usually done is we compute the mean square error. Okay, I should change the notation here. That would be the mean square error. I'm going to change that later. This is mean square error for the first model, for the dynamic, and this is mean square error for the static. Okay. In either case, it's just the squares of the errors divided by the number of errors that we are considering in that measure. Okay. And actually, this is in units squared. So what's going to be more useful is to compute what's called the root mean square error, which will be, in this case, will be the square root of MSE 1. And in this case, the root mean square error 2 will be the square root of the mean square error 2. Okay. We take the square root because that way we have the error in the units measurement, in the same units that we're measuring the phenomena, whatever that is, whether it's dollars, where it's seconds, where it's viscosity, whatever. So that we compute those two figures, and we can compare them and see how large they are depending on the units. Now, what I did is the right thing to do. If we were to do this thing, to compute these things, but using the whole data set to estimate the model, that's not very valid, because that will underestimate the errors. That's why we split the data, and we split it, and we call the data that we're going to use to build the model. We use the training data, and then we're going to test it on the test data, which is going to be the last 6 months or the last 6 days, whatever period I need to forecast ahead. That's what we consider, and don't consider those data points to estimate the model. That's the right thing to do, because otherwise we're underestimating. Okay. So what's advisable is to cut the series, build a model with the part of the series, with the largest part of the series, and then leave out only the observations that we need, that represent the number of periods that we need to forecast ahead in practice. Okay. Now, another thing that's common is to look at the forecast errors as a percentage. As a percentage of the values, okay? And actually, what I always do and recommend we should do is we are going to take, instead of taking the root mean square error 1, and I will concentrate on this one because that's the most useful, using the dynamic simulation. Instead of just looking at the RMSE, I look at the RMSE divided by the average, by the mean of the forecasted observations. Okay. And actually, I can do it, since I know the actual data, I can compute this thing dividing by the mean of the actual future observations. Because I'm splitting the data set, I will compute the mean of the actual observations in the future. So if I'm forecasting 6 periods ahead, I compute the forecasting error, the root mean square error of the forecast, and then divide that by the average of the actual values in the future, and that gives me as a percentage how much I'm deviating from the actual average of the data of the series in the future. Okay, that's another way of doing it, but at least we should compute the root mean square error. Okay, let's see how we're doing. Okay, I'm done here.